All right, to build on what we did last time when we talked about the area bounded between two different curves, but we talked about it very generally speaking with f's and g's in place, I want to do a concrete example where I give you two different curves, one, the equation of the first curve given here, the equation of the second curve given here, and I just ask you how much area is there between the two. And if this were a test, maybe I'd start you out with a graph in case you didn't have a graphing calculator handy. So what that graph looks like is this. Y minus x squared minus 1 equals 0 is pictured in green. 2y minus 4x minus 2 equals 0 is pictured in blue. And you can see that these two curves bound an area kind of in here, this little wedge. And what I want to know is how much area is there in there. I'm no artist, but hopefully this is a good enough picture of what you see over here. So what do we need to know when we're figuring out this area? Well, I guess we need to know their points of intersection because we're going to need to know where we're going to integrate to and from. And you might be asking yourself the question, right, but do I need to know their x coordinates of intersection or their y coordinates of intersection? Well, I purposefully made this problem work out either way. If we decide to integrate with respect to x, then a general approximating rectangle would look something like this. And note that it spans from the blue curve down here to the green curve. And that's true of anywhere in between these two endpoints. If I draw a vertical rectangle, it'll span from the blue curve to the green curve. So what that's saying is one option that I have for figuring out this area is to integrate with respect to x and do the blue minus the green. However, it would also work out in this specific case to use horizontal rectangles to integrate with respect to y. If you look at a generic approximating rectangle drawn horizontally, note that it goes from the green curve to the blue curve. The green curve has the larger x value, the blue curve has the smaller x value. And that's true of any horizontal rectangle in between these two bounds. It would span from green to blue. And so in this case, I can integrate with respect to x or with respect to y. And so what I'm going to do is show you both ways to do it. You're like, why do I need two ways to solve the same problem? Well, what I'll finish this video with is a slight tweak I could do to this problem to make it so that you could not integrate with respect to x and would have to integrate with respect to y, and what that would kind of look like. So without further ado, maybe first we're going to integrate with respect to x. The first thing we need to do is figure out our bounds of integration. And since we're integrating with respect to x, we need to know the x coordinate of these two bounds. So we have two options in terms of how we can figure that out. In this specific case, you might be able to just look at the graph and find what those points are. It looks like this has an x value of 0, and this appears to have an x value of 2. So I guess I'm going to be integrating from 0 to 2. And while that's 100% correct, more generally what you could do is you could solve this system of equations. You could figure out where they intersect by setting these two equations equal to each other and then finding the x coordinates that make them the same. What I'm getting at is when these two curves intersect, their y values are the exact same. Right? The height here is the same in blue as it is in green. The height here is the same in blue as it is in green. So if I solve this equation for y by adding x squared and 1 over to the other side, and I solve this equation for y by adding 4x and 2 over to the other side, and then dividing both sides of the equation by 2, what I now have is an expression that tells me the y value of this curve in green for any given x value. And I have an expression that tells me the y value of the curve in blue for any given x value. And if I want to know when the height of the green curve and the height of the blue curve are the same, well, all I got to do is figure out when x squared plus 1 is the same as 2x plus 1. In other words, solve this equation here. Well, solving this equation, it looks like it's a quadratic, so maybe I can set it equal to 0 and factor. So if I subtract 2x from both sides of the equation and subtract 1 from both sides of the equation, I get here. And to solve this equation, maybe I factor out an x, and I get that x times x minus 2 equals 0. So either x equals 0 or x minus 2 equals 0, in which case x equals 2. And note that these two equations gives me the x value of their intersections, namely 0 and 2. So if I'm going to integrate with respect to x, I'm going to integrate from 0 to 2. And then what I need to do is take the height of the blue rectangles and subtract the height of the green rectangles. Well, to figure out the height of the blue rectangles, what I need to do is know the y coordinate of this curve for any given x coordinate, for whatever rectangle I'm looking at. So what I got to do is I got to solve this equation for y. Conveniently, I've already done that. Similarly, if I want to know the height of a hypothetical green rectangle for some given x value, I would need to solve this equation for y. Again, that's already done. If I'm integrating with respect to x, I solve my two equations for y because that will give me them written as a function of x. And then all I have to do is say, well, the blue one is above the green one in between these two bounds. And I know over here the green one's above the blue one, but I don't care about that. I'm only interested in between these two bounds. So since the blue one's above the green one in between these two bounds, I'm going to take 2x minus 1, and I'm going to subtract x squared minus 1. Note the unnecessary parentheses around 2x plus 1 just to try to help you follow what's going on here. I'm taking this guy and subtracting this guy, and I'm integrating from 0 to 2 with respect to x. This integral is pretty easy, right? A lot of 6.1, the calculus isn't all that hard. What's hard is just kind of setting up the problem. And you could argue that this wasn't that hard to set up, but what you'll see is they get harder and harder. If I want to figure out this integral, maybe first I'll simplify the integrand. So I'll take 2x plus 1 and subtract x squared plus 1. I'll have a negative x squared, and then I'll have a positive 2x, and then plus 1 minus 1 just cancels out. What I'm saying is I need to integrate from 0 to 2, negative x squared plus 2x dx. And that's easy enough. The antiderivative of negative x squared is negative 1/3 x cubed. And the antiderivative of 2x is just x squared. And to evaluate that from 0 to 2 just means taking all my x's and changing them into 2's, which gives me negative 8/3 because 2 cubed is 8, plus 4 because 2 squared is 4. And then I got to subtract what happens when I put in zeros, which you probably don't even need to write that. And what I'm saying is my final answer is just whatever negative 8/3 plus 4 is equal to. Well, 4 is the same as 12/3. So negative 8/3 plus 12/3 gives me positive 4/3. In other words, this area right here is 4/3. And maybe you're like, okay, that wasn't horrible. I mean, it's a little bit new and I'll have to get the hang of it, try some on my own. But I think I can follow all those steps. That's good. But what I want to show you now is a different way to do this, not just to entertain myself, but because I can make different examples where this method that I just showed you won't work. So now what we're going to do is we're going to redo this exact same problem. We'll get the exact same answer, but we're not going to integrate with respect to x. Instead, we're going to integrate with respect to y. If I'm integrating with respect to y, everything changes. I'm not thinking in terms of these vertical rectangles. I'm thinking in terms of these horizontal rectangles. I'm not integrating from 0 to 2, the x coordinates of these points of intersection. I'm integrating from, I think it'll end up being 1 to 5, the y coordinates of these points of intersection. And that 1 and that 5, you could probably get off the graph just like we did here. But maybe more generally, it's worth showing you a method that you can use to solve for those. And the method we'll use to solve for those will be really similar to what we did over here. Over here, I exploited the fact that at these points of intersection, the two curves have the same height. They have the same y values, the same y value between blue and green here, and the same y value between blue and green here. What I'm going to do now to figure out the y coordinates of these points of intersection is I'm going to exploit the fact that at this point right here, the blue curve and the green curve have the same x values. And at this point right here, the blue curve and the green curve have the same x values. So what I can do is I can figure out the x coordinate of this curve by solving this equation for x. Then I can figure out the x coordinate of this curve by solving this equation for x. And then I can set those two equal to each other because, again, at these points of intersection, the curves have the same x values. And if I set those equal to each other, I'll be able to figure out the y coordinates of their points of intersection. So I had y minus x squared minus 1 equals 0. If I want to solve this for x, I could add my x squared over to the other side of the equation and get y minus 1 equals x squared. And here's where things get a little bit tricky. Now I want to take the square root of both sides of the equation to solve for x. But when I take the square root of both sides of an equation, I'm supposed to put in a plus or minus. However, because the x coordinates that I'm interested in my 2 points of intersection here are both over here in the first quadrant, both have non-negative values of x, I don't need the plus or minus. I can just leave this as the positive square root of y minus 1. If my intersections were over here where the x value is negative, then I'd have to worry about the sign in front of this radical. For this equation, since it's linear, it'll be a little bit easier. To solve this equation for x, all I got to do is maybe add the 4x over to the other side and then divide by 4. And that gives me x equals 1/2 y minus 1/2. I now have an expression that tells me the x coordinate of the green curve, an expression that tells me the x coordinate of the blue curve. So what I can do is I can set those equal to each other to figure out the y coordinates at which the 2 points intersect. Setting them equal gives me this equation with only one variable, the letter y. It's kind of a harder equation to solve, but what I can do is I can get rid of this radical by squaring both sides of the equation. So I got y minus 1 equals 1/2 y minus 1/2 squared. And generally when you square both sides of an equation like this, you kind of lose some information. So you can kind of think about, like, if I chose a y value to make this, I don't know, 4, and I chose a y value to make this -4, they're not the same. But when I square both sides, they're both 16. So you got to be a little bit careful when you square both sides of an equation like that. It's a good idea to check your answers at the end and make sure nothing weird happened. Anyways, if I go through solving, I want to get rid of these parentheses. 1/2 y minus 1/2 times 1/2 y minus 1/2. Well, the 1/2 y times the 1/2 y gives me 1/4 y squared. And then the 1/2 y times the -1/2 give me -1/4 y. But then I get another one from the O and the I in FOIL. So I kind of get -2/4 y, or -1/2 y. And then the -1/2 times the -1/2 gives me +1/4. And now to solve this equation, it looks like I have a quadratic trinomial. So maybe I could set it equal to 0 and factor. I could subtract y from both sides and add 1 to both sides. If I subtract y from both sides, instead of having -1/2 y over here, I have -3/2 y over here. And if I add 1 to both sides, instead of having 1/4 as my constant, I have 5/4 as my constant. And you're like, I don't want to factor that. That looks horrible. It's not too bad if you multiply everything by 4 to get rid of the fractions. Multiplying all these terms by 4, 0 times 4 is still 0, so it's still set equal to 0. 1/4 y squared times 4 is y squared. -3/2 times 4 is -12/2, aka -6 y. And then 5/4 times 4 is just this 5. And then I try to factor this by finding two numbers that when I multiply, I get +5. When I add, I get -6. I think y minus 5 and y minus 1 will do the trick in this case. So this tells me that either y minus 5 equals 0 or y minus 1 equals 0. What I'm saying is either y is 5 or y is 1. The y coordinates of these points of intersection are at 1 and at 5. And yeah, I know you could get them from the graph in this specific case, but maybe you can imagine an example where you couldn't get them from the graph and you'd have to solve for them algebraically like we did down here. Wait, what did we just figure out? These are the bounds of integration if I'm integrating with respect to y instead of with respect to x. If I'm picturing a whole bunch of infinitely skinny horizontal rectangles, those rectangles start at a height of 1 and they end when you get up to a height of 5. My integral will go from 1 to 5 and it'll be with respect to y. And then what's going to go inside my integrand? Well, up here, the way I figured out what was inside my integrand is I took the top curve minus the bottom curve. But now I'm not integrating with respect to x, so I don't think about top and bottom curve. I'm integrating with respect to y, so I think about right curve and left curve. I want to take the green curve and subtract the blue curve. And you're like, all right, here's the equation of the green curve. Right, but you don't want this. What you want is something that tells you the x coordinate of the green curve. Fortunately, we just figured that out down here. This tells me the x coordinate of the green curve. For any given y value, it's the square root of y minus 1. And then from that, I want to subtract an expression that tells me the x coordinate of the blue curve. Because again, the blue curve is further left than the green curve. Well, the x coordinate of the blue curve, I don't want to use any of these because these are telling me the y, this tells me the y coordinate of the blue curve. I want to use this expression, which tells me for any y value, the x coordinate is just a half of that y value minus a half. Now we're done with chapter 6 stuff. Right now it's a chapter 5 question. Chapter 5 question is, can you figure out this definite integral? And I think the answer is yes. If we clean this integral up a little bit, we can rewrite the square root of y minus 1 as y minus 1 to the 1/2 power. Maybe that'll make it easier to use the power rule later on. And then take this negative and distribute it through the terms. We get -1/2 y plus 1/2 dy. And then I think we can just take antiderivatives of each of these three terms individually. For this one, you could use a u substitution if you wanted, but things work out really nicely because du would just be equal to dy. I think you might be at the point already where you can just recognize that the antiderivative of y minus 1 to the 1/2 power is 2/3 y minus 1 to the 3/2 power. If not, you could show some extra steps to get there. For this guy, think about your new exponent will be y squared, but you'll need a 1/2 down in front to make everything balance. So you got 1/4 y squared. And then we just add on our variable y in this case to the 1/2 to get 1/2 y. And we need to evaluate this thing from 1 to 5, my bounds of integration, which I forgot to write here and here. Now let's just plug some numbers in and see what happens. If we first plug 5s into this expression, let's see, 5 minus 1 is 4. So I have 2/3 times 4 to the 3/2 power minus 5 squared is 25. And so 25 times negative 1/4 is negative 25/4. And then plugging in 5 here, I get 5/2. And from that, I want to subtract what I get when I plug in 1, where I think things will work out really nicely. Let's see. 1 minus 1 is just 0. So 0 raised to 3/2 times 2/3, that's all just a 0. If I plug in 1 here, I get negative 1/4. And if I plug in 1 here, I get positive 1/2. 4 to the 3/2 power. The 2 means take the square root of the 4, leaving a 2. And then the 3 means cube that thing. So 2 cubed is 8. 8 times 2/3 gives me 16/3. And then negative 25/4 and 5/2. Well, this 5/2, I can think about it as 10/4. So negative 25/4 plus 10/4 is negative 15/4. And then over here, negative 1/4 plus 1/2. 1/2 is 2/4. So negative 1/4 plus 2/4 is positive 1/4. But I want to subtract that positive 1/4. So I get minus 1/4 here. So what do I have here? Well, negative 15/4 minus 1 more fourth is negative 16/4, aka negative 4. So I get 16/3 minus 4. 4, as we saw earlier, is just 12/3. 16/3 minus 12/3 is just 4/3, which might be familiar because it's the exact same answer that we got up here. It makes sense it's the same answer because it's just a different way of thinking about this area that's bounded. But since it's the same bounded area, it shouldn't matter if I figure it out with respect to x or with respect to y. And you're like, wow, that was a lot harder with respect to y than it was with respect to x. It's less intuitive. It doesn't match up with as well with the methods that we learned in chapter 5. I totally agree. You're like, so why are we doing the same thing twice? The reason I could do this either way is because any vertical rectangle in this bounded area would span from blue to green. And any horizontal rectangle in this bounded area would span from blue to green. And for that reason, I'm able to solve this equation for y in terms of x, and I'm able to solve this equation for x in terms of y, and similarly with these equations. But what you'll see is that's not always the case. We kind of got lucky here that vertical rectangles span from blue to green. Remember this example that we had before where vertical rectangles won't span from blue to green. The point is just you really do need to be able to do this both ways because I can change the problems so that you won't be able to do it one way or another. So what you'll have to do with the general problem is look at it and tell, should I integrate with x with respect to x or with respect to y, which is what we'll learn in the next video.